Alright, here's lesson 9.6. Review of basic integration formulas. So this is trying to tie things together from all the units of integration. So there's a summary list at the end of this packet that summarizes all the integration rules you need to know for the AP exam. I'm actually going to hand out some other things that will summarize it so you have a sheet of paper to look at so that you have a few months to remember them. The best way to remember these things is to practice them in questions, not just to try to look at a piece of paper for an hour. Alright, memorizing alone will not be enough. See, integration is not as straightforward as differentiation. To differentiate is sort of follow the recipe. I say you got to be a rule follower. But with integration, you must distinguish among look-alike things so that there's far more thinking involved in terms of what integration rules we have to do compared to differentiating is a lot more straightforward. So success with integration requires memorizing of the formula. So you got to know the rule. You got to recognize which rule to use, obviously. Ability to have some algebra to manipulate things, and then lots of practice. Here we go. How do you not forget? You got to practice every day. Integrate these four look-alike integrals. Although they have similar appearances, they will require you to use three completely different integration formulas, like what we did in class today. All right, here we go. So 1 over 1 plus x squared, that's totally arctangent, the constant on top that you don't see 1. So on the side, if you want, you can write down a square root of 1 is 1, u square root of x squared is x. du square root of x is 1, perfect, it's all set up. The answer is, now, 1 over a is 1 over 1, 1 over 1 is not necessary. Arctan, and then it's u over a, or x over 1, which is just x. That's it, plus the candy. So it's arctangent x plus the candy. Wow, this one looks similar. Now what makes it different is that if we tried to do this as arctan, and you did the square root of x, and then try to take the derivative of the square root of x, like for u prime, I don't know why I said that here, u prime. Anyways, it won't match the numerator. The hook won't match. This is a totally different rule because it's just x, not x squared, taking the square root. And in the numerator, there's no hook for it to match when you try to do the hook. All right, so think of this one. We just said it's 1 plus x to the negative 1. This is a ln rule. And that's it. Don't forget the candy. The derivative of this is 1, so it's already there. Here, notice the derivative of x squared is 2x. So I need a 2 here, undo it. This again is ln. Think of this to the 1. And the 1/2 in front, then make sure the hook is in place. Here. Simple anti-power rule. Add 1 to the exponent, divide by it, and don't forget the candy. Example 2. And again, to be able to distinguish between this, it takes practice, but the numerator is an indicator. Taking the derivative of the denominator to see if it matches the numerator is an indicator. Is it inverse trig, is it ln, or is it the anti-power rule? Keep practicing. All right, how about this one? What's my indicator? Well, the derivative of ln x is 1 over x. That's an indicator to me. Of what direction are we going to go? Now, to write it like this, I realize, okay, the derivative of ln x is 1 over x. Now, this is going to be like, all right. Think of ln x here. I'm going to write it this way. I know it's going to feel a little bit awkward at first. Think of it as it's the negative 1. The hook is already there because the derivative of ln x is 1 over x. If you add 1 to the exponent, you get 0. So the integration of ln x is the ln of ln x. So it's ln x plus the candy. Practice. This one looks similar. what's different about this one, again, I see the hook. So the derivative of ln x is 1 over x. Think of this to the power of positive 1. Now if it's to the power of positive 1, what's the anti-power rules? I can then add 1. 1 plus 1 is 2. Divide by it. And don't forget the candy. What makes this different? Well, when I add 1 to negative 1, I get 0 divided by 0. That's a special rule, ln, to integrate that. Here I can add 1, no problem. That's 2 and divide by 2, not the special rule. All right, these are the simplest algebraic techniques that we have used to fit integrals into forms which appear in the basic integration formulas. So we've expanded things. We've done division by a monomial, dividing long division to be able to separate things. That's when the numerator has a degree that's the same or more. There it is. The degree of the numerator is the same or more. Or by splitting or separating the numerator. Now, the more complicated, harder to see techniques will be discussed in the final lesson of 9-7. I bet you can't wait. So, here are some examples again to practice. Here's an example where I'm going to expand. So literally I'm going to do this. Algebra. So e to the 2x times e to the 2x. Add the exponents. That's 4x. Foiling, if you like. Negative 2 times e to the 2x, negative 2 times e to the 2x. How many negative 2 to the ex's do we have? So negative 4 e to the 2x when you combine like terms, when you FOIL, and then negative times the negative is positive. Now integrate. Each one, remember when you see adding or subtracting, just look at each one separately. So e to the 4x, the hook is 4. So to undo it, I need 1/4 e to the 4x. Here, e to the 2x, the hook is 2, but I have a 4 in front, so I need a 2 to make it equivalent when I integrate it. And then 4 is just 4x. And don't forget the candy. So some algebra to expand and then be able to use the rules. Here, oh, I see this monomial. That's a big old indicator right away. Then I'm going to divide by it. Now, if I take each one separately, this is what it would look like. So it's x over root x, simplify it, minus 2 root x over root x, simplify it, plus 1 over root x, simplify it. So I haven't integrated yet. So this is like 1 over 1/2. So when I subtract, that's x to the 1/2. The root x is crossed out, that's minus 2. And then 1 over root x is simply x to the negative 1/2. I make sure I write it as exponents. I don't want radical signs. I don't want fractions. Now I can integrate. Power rule. Add 1. That's 3 over 2. And then divide. Or you can do the reciprocal. Again, that's just 2x, add 1, divide, or the reciprocal, and then don't forget the candy. So 5, I'm sorry, the degrees are the same. We're going to divide x squared plus x into x squared minus x minus 1. It goes once. Subtract the remainder, be careful, is negative 2x, bring down the negative 1. Notice in this case the degree here is bigger than here, so I'm done dividing. When what you're dividing by is the degree is bigger than what's going into. So the answer is 1. And then the remainder is negative 2x minus 1 over x squared plus x. Now, the integration of 1 is just x. You can do this separately. Notice the denominator here. What's the derivative of x squared plus x? It's 2x plus 1. That's almost what I have here, right? 2x plus 1. Well, what would happen if I take that negative and I integrate it out front, that constant, that negative 1, if I divide it out? Can you see now how the denominator can match the numerator? The derivative of x squared plus x is already there. This is a ln, ln. And the hook is already there. One more, and it's going to be practice. Number 6. Can you integrate this? That square root makes that whole denominator like a monomial. So I'm going to separate as 3 over the square root of 1 minus x squared, yes, arc sine, minus x over the square root of 1 minus x squared, not arc sine, because of the x. So this is arc sine. So on the side, let me just separate here so I have some room. A is 1, u is x, u prime is 1. This 3 I can just put in front. So this is 3 arc sine x over 1, or just x. Here, the derivative of negative x squared is negative 2x. So I need a negative 2x here. Then I'm going to change it to, so it stays the same. Because I need a negative 2x, I need to make a plus here so it stays the same as it was before. And also what do I need? Oh, I need a 1/2 too. So I need that plus and a 1/2. That way what it was before stays the same. So when you multiply them together, the answer is still negative, and it still has that x, that negative in terms of the adding. All right, now we can do the anti-power rule. So if I just think of that denominator, think of it as 1 minus x squared to the negative 1/2. The hook's already there. Add 1 to the exponent. That 1/2 is going to be in front here. So anyways, add 1 to the exponent, that's 1/2. Divide by 1/2 or times the reciprocal, and then the candy. So this 1/2 comes from here. That 2 comes from adding 1 and then dividing by 1/2. All right, number 7 and 8. You separate the numerator to create basic integration forms in example 6. Do not make this error. We've talked about this in class. Bad algebra, not a binomial on the bottom. Binomial, you can't separate it like that. So don't do that. So how would you integrate this problem? So can you see the u and the u prime? So when I look at the hook here, what's the derivative of cosine? Is negative sine. So when I see e to here, what's the hook here? So I can see u and u prime. Well, the derivative of cosine is sine, but it's negative sine. And the derivative of 2 is 1/2. So if I would set this up right, I need a negative and a 2. I haven't integrated yet. And then how do I make them equivalent? Is I need a 1/2 in front. I need a negative 1/2. So a negative times a negative keeps that positive. Now I can integrate it. So all of this is taken care of with this. So the rule for e is e to whatever, and then the negative 1/2 in front. And don't forget the candy. Last one, and then practice, practice, practice. 8. Recognize what's the derivative of this, or integrate, and so on. So what's the derivative of tangent? It's secant squared. So think of it like this. Tangent, like that. And the derivative of that is that. That's my little indicator myself. This is actually in the form of arctangent, with the tangent inside of it, just to confuse you. So, a, the square root of 9 is 3. U, the square root of this, they undo each other, so this is tangent x. And then u prime, the derivative of tangent is secant squared. Well, see how the hook is already there for it. So then we follow the rule for arctangent. So the rule is u over a, or sorry, 1 over a, which is 1/3. Then arctan, then u over a, tangent x over 3, and then don't forget the candy. There it is. Now we have to practice.